This video is going to talk about op-amp imperfections and also give a practical op-amp integrator on the scope. So first of all, the three op-amp imperfections you'll hear about are offset voltage, bias currents entering the terminals, and the difference between those bias currents. And we can model that as an ideal op-amp inside of this op-amp with all these imperfections added. And if we know that the output is some large amplification times the difference between the voltage of the pins, it makes sense if we define that error voltage between the pins here, because then the offset voltage, when we take our true output versus here, affects our transfer function. So we can see here, because of the presence of this offset voltage, our error voltage needs to be in the opposite polarity for this to actually have 0 volts across it and us to get the 0 output. Also, you'll see that this is written as I offset over 2 because it's convenient to define the current entering the pins as the same numeric value. And then the difference would be added to those. So for instance, if one pin has a 10 microamp current bias, the other pin has an 8 microamp, then the offset is 2 microamps. But if we define a new bias as 9, then I bias entering each of these is 9, and there's a 1 microvolt offset that's adding to one and subtracting from the other to actually give the true 8 and 10 microamp. For example, we're going to find the error voltage for a simple non-inverting op-amp configuration due to all three of these sources. And use superposition, so you solve for one, short out voltage sources for the other, or open current sources for the other, and then repeat and sum the total. And the reason for the offset currents is because the input of op-amps are transistor stages, and even though in FET-based op-amps the current is in the picoamps, for BJTs it might be a little bit more non-negligible. And here we, if we start out with finding the voltage offset, we see if we just place it at the non-inverting terminal, then we have a non-inverting equation for that offset. So it's pretty easy. It's just the voltage appearing here times 1 plus R2 over R1. So now let's solve for the bias current, or the offset caused by the voltage output caused by the bias current. And we were shorting out offset voltage because we're using superposition. And if we notice that because we're shorting that offset voltage, if this pin is grounded, that means this pin is also grounded. And that means there's no voltage drop across this R1 resistor, which means there can't be any current flowing through it. So all the bias current, since these are equal, has to be flowing from R2. So that means the voltage error due to I bias is just IB times R2, not anything to do with R1. Now for I offset over 2, similarly, there's no voltage across R1, so it's just I offset over 2 R2. And to give you an example of some real life values for these, in the data sheet for TL081, it gives you input offset voltage, typical, here's 20 millivolts max for this model. Input offset current, input bias current. And for these, the max is 10 nanoamps, so 10 to the minus 9th for the full range, but in general, you'll have much less than that, 400 picoamps for the bias current, and the offset current is 200 picoamps. And that's because this is actually a JFET op-amp, so it draws much less current than these BJT one I've drawn here. And yeah, I just wrote down the values here. If you take the total error with, let's say, both of these resistors are 1 meg, then you get about a 30 millivolt offset, which could be significant if you're trying to amplify low voltage stuff and amplify it a lot. Might be sensitive to noise. So it turns out we can actually remove the offset voltage caused by the bias current if we produce an equal voltage at the plus and minus terminals, then that's just a common mode voltage, and op-amp won't amplify that. It won't, because there's no difference between the terminals. And the way we do that is if we just solve for what would make V out equal to 0. We see, let's take a Thevenin equivalent for these two resistor values. Notice we shorted this terminal because we're solving for what makes V out 0, so we can treat this as a short. And now after we take the Thevenin, we see that we have some bias current entering from here and another bias current entering from here. Clearly, if this unknown resistor value R is the parallel combination of these, then the voltage drop across these two will be the same. So just placing a resistor here equal to the parallel combination of these two would cancel the bias current offset. And yeah, there's no effect to the original circuit because ideally this draws no current. So for large signal applications, this is still, you see the full voltage input signal at the non-inverting terminal. A more complicated example is an inverting integrator, and it's clear if you use impedance division for the impedance of this over the impedance of this, then we have an output transfer function of this. And let's look for the output error like we did before for all three sources. So let's start with V offset. First way you can do it is we've placed it at one pin here, and we know we can just use impedance division again. So it's 1 plus R2 over R1, because now we're treating this as a non-inverting configuration. Before, for inverting, you know, it's minus Z2 over Z1 is a transfer function. And that was because we had our input into this pin. But now if we treat the offset as entering this pin, we can use non-inverting. And we get 1 over C, or we get V offset times quantity 1 over C, 1 over S, 1 over R. And in the Laplace domain, 1 over S is an integration. So we can get this. Alternatively, we recognize that the current through this resistor here is just V offset because the same voltage appears at both pins over that resistance. And since no current is flowing into the terminals, that means that whole current has to be flowing through this capacitor. And that means that we are integrating because constant current into a capacitor is in a linear increase, so integration of a constant. And we know the output seen is V offset because initially the voltage across the capacitor is 0. So at that instant, we're going to see V offset, and then plus the voltage caused by that constant current ramp entering, and you get the same exact thing as before. And now let's look at bias currents. So at DC, the impedance of the capacitor is infinite for DC. So we can treat it as just the bias current flowing through these resistors here. And again, just as the previous example, the current is the same through these. We're calling R here the same as R, so they're nulled out. The net contribution is same voltage at each pin, so it's not going to amplify any difference. Error 0. For I offset over 2, we know similarly the voltage at the non-inverting terminal is I offset over 2 times R. We know that this current here times R has to be the same voltage as I offset 2 over R. And that means that Ix is I offset over 2, but in this direction. So now we have a total of I offset over 2 here flowing left, I offset over 2 flowing down, which means we have the sum of those is just 1 I offset flowing into this capacitor. So again, we're going to have an integration operation here. And yeah, as before, we're going to see the instant this happens, we're going to have a DC value here. So that's what this term is. And then since the voltage across the capacitor starts at 0, then it ramps up, which is this. And this is a ramp, so as t is bigger, our slope is increasing. So that's not good. We don't want any ramps if we're trying to leave this in here for a while. So Practical Integrator has a feedback resistor as well. And if the feedback resistor impedance is much more than 1 over SC, or the impedance of the capacitor, then we can treat this, if we just do impedance division, as this impedance combination over this impedance, then it's basically an integration. This should be, the input should be over here, since we're doing inverting integrator. And we keep this resistor here because this will null out the bias currents, as we proved before. So yeah, if we take a look at this here, bias currents are 0. Now what's the contribution of the error due to I offset over 2? Before, without this resistor, we had a possibly infinite error because of this ramp. And now we see, if we just use node voltage and follow these equations, it's just I offset times the feedback resistor. So there's a trade-off. If RF is big, then this is treated more as an ideal integrator, but now your error is slightly larger. And as before, we can treat the error due to V offset as just a non-inverting op-amp amplification, because at DC, this capacitor is open. So it's 1 plus RF over R. Here what I have on the scope is configuration like so. Wanted a tau of about half a millisecond, and I'm just using a 1K resistor for R1. I'm using about a 10K for R2, which means the parallel is basically just 1K, so that's what I have for RX as well. For C, that means I need a half a mic cap here. I'm really using two 24 nanofarad ones in parallel, which gets me almost there. So for sinusoidal input, tau would be how long it, how much attenuation you're getting, because if we recall our output voltage equation, V out is 1 over tau times the integral of what your input signal is. So here, as your input signal increases in frequency, the integral of that divided by 1 over the frequency. And we see we're going to attenuate much more for higher frequencies. But what if it's a square wave input? Well, as tau goes up, the amount of time the integration takes goes up, which means it's slower, which means our slope is not as large. So here, what I have on the scope is a 1.5 peak-to-peak input in the blue, and that means about 0.75 above or below 0. And if I calculate what the output should be, which is in the yellow, it's 1 over tau times Vn times t, where t is the length of time it's either high or low. So if I actually plug that in, here's the tau I have, here's the input signal, and here's the width of half a period, and we should see about 1.15 volts on the rise, and that is what we see here in the yellow. And if I take away one of these two 224 nanofarad caps in parallel, that means our tau will be cut in half. And if our tau is cut in half, that means we should double our peak-to-peak by the time we're done integrating. And let's do that here. Yeah, so that's about here it is again, with it and without it. See, my function generator doesn't do well with changing load impedance. But yeah, there it is.